Capturing wind energy requires a collision. We are forcing rigid mechanical engineering to extract power from a chaotic fluid environment. The engineering problem is one of conversion, intercepting a linear mass of moving air and turning it into localized rotational torque. This 3D representation shows a moving column of air. The available power within it is defined by the kinetic energy equation for wind, which relies on the mass of the air passing through and the square of its velocity. Into that kinetic energy requires placing a mechanical boundary directly in the path of the fluid. Before we can engineer the physical machine, we must calculate the absolute mathematical ceiling of the energy available within the fluid itself. This diagram abstracts the physical turbine into a two-dimensional actuator disc, positioned inside a stream tube of moving air particles. According to the principle of mass continuity, the mass flow rate entering the system upstream must perfectly equal the mass flow rate exiting the system downstream. This line graph charts the air velocity. As the disk extracts kinetic energy, it physically slows the wind velocity. To maintain equal mass flow, the slower downstream air has to spread out, causing the stream tube to expand. A second graph overlays the inverse effect on pressure. As air hits the rotor plane, pressure spikes up, then instantly plunges below ambient levels on the other side, before gradually recovering. Attempting to extract 100% of that kinetic energy creates a physical paradox. Mathematically, extracting all the energy would drop the downstream wind velocity to exactly zero. A zero velocity downstream creates a wall of stationary air. It acts as an impenetrable physical blockage, halting the flow of all upstream air through the rotor. Power generation requires a mandatory compromise. You must slow the wind down enough to extract energy, but let it flow fast enough to clear the rotor plane. In 1919, physicist Albert Betz published a mathematical proof governing this exact balance of extraction. Betz proved that peak power generation only occurs at a specific velocity drop ratio. The downstream wind speed must be reduced to exactly 1/3 of the upstream speed. Engineers measure this extraction efficiency using a metric called the power coefficient, or CP. Factoring in Betz's optimal ratio, the absolute theoretical maximum of this coefficient calculates to 59.3%. No future material science or engineering breakthrough can bypass this thermodynamic limit. Betz's limit forms the unyielding ceiling of wind power. Modern engineering is a quest to design physical shapes that get as close to 59.3% as reality allows. To understand how we extract that energy, we have to move from the abstract column of air to the physical shape of the rotor blade interacting with it. Modern turbines do not act like sails. They do not operate via drag by simply blocking the wind. The blades are highly optimized airfoils, generating mechanical torque almost entirely through aerodynamic lift. In this 2D cross-section, the true wind velocity vector, VW, acts linearly, pointing directly at the leading edge. But as the blade moves, we must account for the rotational velocity vector, VR, generated by its circular movement. These forces synthesize to create the relative wind velocity, or VREL. The diagonal aerodynamic force the blade experiences is a fusion of the true wind and its own rotation. The blade's rotation speed introduces a major mechanical complication. Rotational velocity increases linearly the further away you move from the central hub. The tip travels exponentially faster than the root. Because of this escalating rotational speed, the relative wind velocity angle shifts drastically along the entire length of the blade. To generate lift without stalling, an airfoil must maintain a precise angle of attack relative to the oncoming wind. A perfectly straight blade presents a structural problem. It maintains a functional angle of attack at the slow root, but completely stalls at the fast-moving tip. Solving this aerodynamic problem requires a continuous physical twist built directly into the blade's mold. The thick root of the blade must be pitched aggressively into the oncoming weather to catch the dominant true wind. Moving outward, the tip of the blade must flatten out entirely to cut through the dominant rotational wind it creates itself. A single blade is actually a continuous series of distinct, precisely angled airfoils, mathematically stacked to extract uniform torque across a chaotic gradient of velocities. This X-ray rendering takes us inside the nacelle casing at the top of the tower to track that newly generated torque. Inside, there is a severe mechanical mismatch between the aerodynamic rotor in the front and the electrical generator in the rear. The rotor is constrained by size. It must turn at a very slow RPM to prevent the massive sweeping blade tips from breaking the speed of sound. The generator is constrained by frequency. Standard induction generators require extreme rotational speeds to output alternating current that syncs with standard 50 and 60 Hz electrical grids. The planetary gearbox serves as the heavy-duty translation mechanism, linking these incompatible speeds. A slow-turning input shaft drives planetary gears that mathematically multiply the rotation, outputting into a rapidly spinning high-speed shaft. The drivetrain's purpose is to sacrifice pure aerodynamic torque in exchange for intense rotational velocity, bridging the final gap between physical force and usable electrical power. This highly calibrated system remains deeply vulnerable during extreme weather events. When winds reach a specific operational threshold, the kinetic energy threatens to exceed the structural load limits of the gearbox and the composite blades. The primary survival mechanism is active pitch control. The entire massive blade mechanically rotates on its longitudinal axis to shed aerodynamic lift and intentionally stall the rotor. At operational extremes, power generation becomes a liability. The machine must deploy an active mechanical defense to survive the violence of unconstrained fluid dynamics. Pulling back, we can trace the complete, uninterrupted pathway of energy transfer. The entire energy chain operates beneath the absolute fluid dynamic ceiling of Betz's law. Aerodynamic capture extracts power using highly precise blade twist and lift vectors. The internal drivetrain translates that heavy physical torque into precise electrical grid synchronization. All future advancements in wind energy, from lighter composite materials increasing sweep areas to massive direct drive generators, are compounding engineering strategies. They are all designed to inch a fraction of a percent closer to an unyielding theoretical law of physics.